Light is everywhere. You see it every single day. And after 400 years of scientific investigation, the greatest minds in physics still cannot agree on what it actually is. This is not an exaggeration. This is not sensationalism. This is the honest truth that kept Einstein awake at night. What you're about to hear will challenge everything you think you know about reality itself. Chapter 1. The question that changed everything. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. What you're about to hear will challenge everything you think you know about reality itself. We're going to explore the single most studied phenomenon in the history of science. Something so common that you experience it every waking moment of your life. Something so mysterious that after 400 years of investigation, the greatest minds in physics still cannot agree on what it actually is. Light, the glow from your screen, the warmth on your face from a distant star, the colours of a sunset painting the sky in shades no artist can truly capture. We see it. We feel it. We depend on it for our very survival, and we have absolutely no idea what it really is. This is not an exaggeration. This is not sensationalism. This is the honest truth that physicists have struggled with since the dawn of modern science. Light behaves in ways that defy logic. It breaks rules that should be unbreakable. It seems to know things it cannot possibly know, and when we try to observe it too closely, it changes its behavior as if it is aware we are watching. The story we are about to tell spans centuries. It involves some of the greatest scientists who ever lived: Isaac Newton, Thomas Young, James Clerk Maxwell, Albert Einstein, Niels Bohr, Richard Feynman. Each of them grappled with light. Each of them made revolutionary discoveries, and each of them ultimately had to admit there was something about light they could not explain. Let us start at the beginning. Not the scientific beginning, but the human beginning, the moment our ancestors first wondered what makes the world visible. Imagine the ancient world, a time before electricity, before glass lenses, before any understanding of physics as we know it today. The sun rises and the world awakens. The sun sets and darkness falls. What is this power that creates visibility itself? What is this force that separates day from night? The ancient Greeks were among the first to seriously consider the question. Empedocles believed that light flowed from our eyes like invisible rays that touched objects and allowed us to perceive them. Plato refined this idea, suggesting that fire emanated from our eyes and merged with daylight to create vision. Aristotle disagreed entirely. He proposed that light was not a substance at all, but rather a quality of the transparent medium between objects and the eye. None of them were right. But they were asking the right questions. What is light made of? How does it travel? Why does it behave the way it does? These questions would remain unanswered for 2,000 years. Then came the 17th century, the age of reason, the birth of modern physics, and two titans of science who would define the debate about light for generations to come. Isaac Newton was perhaps the greatest physicist in history. His laws of motion and universal gravitation revolutionized our understanding of the physical world. When Newton turned his attention to light, he performed a famous experiment. He directed a beam of sunlight through a glass prism and watched it separate into a rainbow of colors: red, orange, yellow, green, blue, violet. White light, he realized, was not pure at all. It was a mixture of all colors combined. But what was light itself? Newton had an answer. Light, he declared, consists of tiny particles. He called them corpuscles. These corpuscles traveled in straight lines at enormous speed and bounced off surfaces like tiny bullets. This explained reflection perfectly. A ball thrown at a wall bounces back. A corpuscle of light thrown at a mirror does the same. Newton's reputation was unassailable. When Isaac Newton declared that light was made of particles, the scientific world largely accepted it as fact. Who would dare contradict the man who had explained the motion of the planets? But there was a problem. Actually, there were several problems, and they would eventually bring Newton's particle theory crashing down. The first problem was shadows. If light consists of particles travelling in straight lines, then shadows should have perfectly sharp edges. But they do not. Look closely at any shadow, and you will see the edges are slightly fuzzy. The darkness gradually fades into light rather than cutting off abruptly. Particles cannot explain this. The second problem was something called diffraction. When light passes through a tiny opening, it does not simply continue in a straight line. It spreads out. It bends around corners. It creates patterns of light and dark bands that seem impossible if light is just a stream of tiny bullets. But the biggest problem of all was interference. If you send two beams of light to the same spot, they should add together and create a brighter light. Particles would pile up. More particles means more light. Simple. Except that is not what happens. In certain conditions, two beams of light can cancel each other out. Light plus light equals darkness. How can particles do that? They cannot. But waves can. Think of water waves in a pond. If two waves meet crest to crest, they combine and create a larger wave. But if a crest meets a trough, they cancel each other out. The water goes flat. This is called interference, and it is a property exclusively of waves. Even during Newton's lifetime, there was a rival theory. The Dutch scientist Christian Huygens proposed that light was not made of particles at all, but rather was a wave. Light waves rippled through space just as sound waves ripple through air and water waves ripple across the ocean. Huygens could explain diffraction. He could explain the fuzzy edges of shadows. He could explain why light bends when it enters water or glass. The wave theory seemed to answer questions that the particle theory could not, but Newton was Newton. His authority was overwhelming. And Huygens could not explain one crucial thing. Waves need a medium. Sound waves need air. Water waves need water. What medium could light waves possibly travel through? The space between the Earth and the Sun is empty vacuum. If light is a wave, what is waving? Huygens proposed an invisible substance called the luminiferous ether. This ether supposedly filled all of space. It was so thin and so perfect that it offered no resistance to the motion of planets, yet it was rigid enough to transmit light waves at incredible speed. It was a convenient but unsatisfying answer. The ether seemed to be invented, specifically to save the wave theory without any actual evidence that it existed, and so Newton's particle theory prevailed. For nearly 100 years after his death, scientists assumed that light consisted of corpuscles. The wave theory was all but forgotten. Then something remarkable happened. In the year 1801, a young English physician named Thomas Young performed an experiment so simple and so profound that it would eventually reshape our entire understanding of the universe. We will explore that experiment in detail in the next chapter, but for now understand this. That experiment proved beyond any reasonable doubt that light is a wave. Newton was wrong. The particle theory was dead, or so everyone thought. Because a century later, a young patent clerk in Switzerland named Albert Einstein would bring the particles back. Light, he would prove, is also made of particles, not instead of waves. In addition to waves, light is somehow both at the same time wave and particle, continuous and discrete, spread out and localized. This is called wave-particle duality, and it makes absolutely no sense. Not in any intuitive way, not in any classical way, not in any way that fits with our everyday experience of the world. How can something be two contradictory things at once? How can light spread out like a wave and strike a detector as a single particle? How can it interfere with itself when no one is watching and then behave like a normal particle when someone looks? These questions are not merely academic puzzles. They strike at the heart of what we mean by reality. They challenge our assumptions about cause and effect. They suggest that the universe at its most fundamental level operates according to rules that human beings were never evolved to understand. Richard Feynman was one of the greatest physicists of the 20th century. He won the Nobel Prize for his work on quantum electrodynamics. He spent decades thinking about light and how it behaves. And here is what he said about the famous double-slit experiment, the experiment that reveals light's true nature. He said it contains the only mystery of quantum mechanics. He said it is a phenomenon which is impossible to explain in any classical way. He said it has in it the heart of quantum mechanics. The only mystery. Think about that. Quantum mechanics is filled with strange and counterintuitive phenomena. Particles that tunnel through barriers, objects that exist in multiple states simultaneously, measurements that seem to affect distant particles instantaneously. And yet, Feynman said the double-slit experiment contains the only mystery. Because if you truly understand the double-slit experiment, you understand the fundamental weirdness at the core of reality. And if you think you understand quantum mechanics, Feynman also said, then you do not understand quantum mechanics. That is where we are going. Into the heart of the mystery, into the phenomenon that no one can explain, into the question that has haunted physics for over 2 centuries. What is light? We will begin with Thomas Young and his revolutionary experiment. We will watch him prove that light is a wave and overturn a century of scientific consensus. Then we will follow James Clerk Maxwell as he unifies electricity, magnetism, and light into a single elegant theory. We will see Albert Einstein resurrect the particle in a paper that would win him the Nobel Prize. We will witness the bizarre reality of quantum mechanics as single photons somehow interfere with themselves, and then we will go deeper, into experiments where the act of observation changes outcomes, into entanglement where particles remain connected across any distance, into the delayed choice quantum eraser where it seems like the future can affect the past. By the end of this investigation, you will not fully understand light. No one does. But you will understand why it is so deeply mysterious. You will understand what we have discovered and what still defies explanation. And you will never look at the world quite the same way again. The journey begins now, in 1801, in a darkened room in London, where a young physician is about to challenge Isaac Newton himself and change physics forever. Chapter 2. A Wave That Refused to Behave London. 1801. The streets are lit by flickering gas lamps. The Industrial Revolution is transforming England. Steam engines rumble through the countryside. New machines produce goods at unprecedented rates. The world is changing faster than anyone alive has ever witnessed. In the midst of this transformation, a 30-year-old physician is about to conduct an experiment that will overturn a century of scientific certainty. His name is Thomas Young, and he is not satisfied with simply accepting Isaac Newton's proclamation that light consists of particles. Young is a polymath. He speaks at least a dozen languages. He helped decode the Rosetta Stone and made crucial contributions to deciphering Egyptian hieroglyphics. He studied medicine in Edinburgh, Göttingen, and Cambridge. He investigated the mechanics of the human eye and discovered how our lens changes shape to focus on objects at different distances. He is brilliant, curious, and utterly unafraid to challenge established authority, including the authority of Isaac Newton. Young has been thinking about light for years. He has observed phenomena that the particle theory cannot explain. He has read the work of Christian Huygens. He believes that light might actually be a wave after all. But believing is not enough. He needs proof. And so he designs an experiment, simple in concept, profound in implications, revolutionary in its results. Young takes a beam of sunlight and directs it toward a barrier with 2 narrow slits cut into it. Just 2 parallel openings. Nothing more. On the other side of the barrier, he places a screen where he can observe what happens to the light after it passes through the slits. If Newton is right and light consists of particles, then the result should be straightforward. Particles will pass through one slit or the other and pile up in 2 strips on the screen. 2 bright bands corresponding to the 2 openings. Simple, predictable, and completely consistent with particles travelling in straight lines. But that is not what Thomas Young sees. Instead of 2 bright strips, Young observes a pattern of alternating light and dark bands. Bright, dark, bright, dark, bright, dark. A series of parallel lines spreading across the screen. Not 2 spots of light, but many. Not a simple pattern, but a complex one. Young recognizes this pattern immediately. He has seen it before, in water. Think of a calm pond. Drop 2 stones into the water side by side. Each stone creates ripples that spread outward in circular waves. Where 2 crests meet, the waves combine and create a higher peak. Where a crest meets a trough, they cancel out and the water goes flat. The result is a complex pattern of reinforcement and cancellation spreading across the pond. This is interference, and it is exclusively a property of waves. Particles cannot interfere with each other in this way. Tennis balls do not cancel out when they collide. Bullets do not create alternating patterns when fired through 2 holes, but light does. Young has proven beyond doubt that light is a wave. The interference pattern on his screen is exactly what wave theory predicts. The mathematics match perfectly. The bright bands appear where waves from the 2 slits arrive in phase. Crest meeting crest, trough meeting trough. The waves reinforce each other and create brightness. The dark bands appear where waves arrive out of phase. Crest meeting trough. The waves cancel each other and create darkness. Young presents his findings to the Royal Society in 1803. His paper is titled On the Theory of Light and Colours. It contains not only his experimental results but also a clear explanation of how interference works. He even calculates the wavelengths of different colours of light. Red light has a longer wavelength, violet light has a shorter one. The full spectrum corresponds to different wavelengths of the same fundamental phenomenon. The reaction from the scientific establishment is hostile. Newton has been dead for 76 years, but his reputation remains sacrosanct. How dare this physician claim to know more about light than the greatest physicist in history? The critics are merciless. One particularly vicious attack published anonymously in the Edinburgh Review calls Young's work destitute of every species of merit. The review accuses him of presenting the unmanly and unfruitful pleasure of a boyish and prurient imagination. Young is wounded by these attacks. For a time, he stops publishing on the subject. The weight of Newton's authority combined with the viciousness of the criticism is too much to bear, but the truth cannot be suppressed forever. In France, a civil engineer named Augustin Jean Fresnel independently develops a comprehensive mathematical theory of light waves. Fresnel's work is more rigorous than Young's. He derives precise equations that predict exactly how light will behave when it passes through openings around obstacles and through different materials. In 1818, Fresnel submits his wave theory to the French Academy of Sciences for a prestigious prize competition. One of the judges is Simeon Denis Poisson, a brilliant mathematician and a firm believer in Newton's particle theory. Poisson studies Fresnel's mathematics looking for flaws. He finds one. Or so he thinks. According to Fresnel's equations, if you shine light on a small circular disk, a bright spot should appear at the exact centre of the disk's shadow. This seems absurd. How can there be a bright spot in the middle of a shadow? Poisson believes he has discovered a fatal flaw in the wave theory, but another, member of the committee Dominique François Jean Arago, decides to actually perform the experiment. He shines light on a small circular disk, and there it is, a bright spot at the exact centre of the shadow, exactly where Fresnel's wave theory predicted it would be. The bright spot becomes known as Poisson's spot or Arago's spot. It is direct experimental confirmation of wave theory derived from the very prediction meant to disprove it. Fresnel wins the prize, and the particle theory of light collapses. By the 1830s, the wave theory has triumphed completely. Scientists across Europe accept that light is a wave phenomenon. Young is vindicated, Newton is proven wrong. A new understanding of a light takes hold. But questions remain. If light is a wave, what exactly is waving? Sound waves are vibrations of air molecules. Water waves are oscillations of water particles. What is a light wave made of? What medium carries it across the vast emptiness of space from the stars to our eyes? The answer comes from an unexpected direction, not from experiments with light, but from experiments with electricity and magnetism. In 1831, Michael Faraday discovers electromagnetic induction. He shows that a changing magnetic field can create an electric current, and a changing electric current can create a magnetic field. Electricity and magnetism, it turns out, are deeply connected. Faraday is a genius experimentalist, but he lacks formal mathematical training. He cannot express his discoveries in equations. He thinks in terms of invisible lines of force spreading through space. Beautiful, intuitive, but not rigorous enough to satisfy mathematicians. Enter James Clerk Maxwell. Maxwell is Scottish. Born in Edinburgh in 1831, the same year Faraday makes his discovery. Maxwell is the opposite of Faraday. He is a mathematical prodigy. He thinks in equations. He can translate physical intuition into precise mathematical language. Maxwell becomes fascinated by Faraday's work. He sets out to express Faraday's ideas in mathematical form. The project will take him decades, and when he finally completes it, he will have done something far more profound than simply translating between languages. Maxwell will discover that light itself is electromagnetic. In 1865, Maxwell publishes his masterpiece, A Dynamical Theory of the Electromagnetic Field. In this paper, he presents a set of equations that describe the behavior of electric and magnetic fields. These equations, now known as Maxwell's equations, are among the most beautiful and powerful in all of physics. But hidden within these equations is a stunning prediction. Maxwell's mathematics shows that oscillating electric and magnetic fields can propagate through empty space as waves. One field creates the other, which creates the first, and so on, in an endless dance, moving through the vacuum at a specific speed. Maxwell calculates this speed. He uses measurements of electrical and magnetic constants that have nothing to do with light. Pure electrical and magnetic quantities measured in laboratories. The answer comes out to approximately 300 million meters per second. Maxwell recognizes this number immediately. It is the speed of light. The coincidence is too precise to be accidental. Maxwell draws the inevitable conclusion. Light, he writes, consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. In other words, light is an electromagnetic wave. This is one of the greatest unifications in the history of science. Electricity, magnetism, and light. Three seemingly separate phenomena revealed to be aspects of a single underlying reality. The flash of lightning, the pull of a magnet, and the glow of a candle are all manifestations of the same fundamental force. Maxwell predicts that other electromagnetic waves should exist, waves with longer wavelengths than visible light, waves with shorter wavelengths, an entire spectrum of electromagnetic radiation waiting to be discovered. Maxwell dies in 1879 at the age of 48. He does not live to see his prediction confirmed. That confirmation comes 8 years later. In 1887, Heinrich Hertz, a German physicist, generates and detects radio waves for the first time. These waves travel at the speed of light. They behave exactly as Maxwell's equations predict. They are invisible electromagnetic radiation with wavelengths longer than infrared light. The electromagnetic theory of light is proven correct. Maxwell's equations become the foundation of all modern electromagnetic technology: radio, television, radar, microwave ovens, cell phones, Wi-Fi. Everything that uses electromagnetic waves owes its existence to Maxwell's insight. The nature of light seems settled. Light is a wave, an electromagnetic wave, a self-propagating disturbance in the electric and magnetic fields that pervades all of space. The debate between particles and waves that began with Newton and Huygens is finally resolved. Or so everyone believes. Because lurking in the laboratories of late 19th century physics are experimental results that Maxwell's beautiful theory cannot explain. Strange phenomena involving light interacting with matter. Patterns that make no sense if light is a continuous wave spreading through space. The most troubling of these phenomena is called the photoelectric effect. Scientists shine light on metal surfaces, electrons fly out. This is not surprising. Light carries energy. Energy can knock electrons loose. Simple. But the details are wrong. All wrong. According to wave theory, the intensity of light should determine how much energy is delivered to the electrons. Brighter light means more energy. More energy means faster electrons. Simple, obvious, and completely incorrect. The experiments show something different. The speed of the ejected electrons depends not on the intensity of light, but on its frequency. Blue light ejects faster electrons than red light regardless of how bright the light is, and below a certain frequency no electrons are ejected at all, no matter how bright the light, no matter how long you shine it on the metal. Nothing. This makes no sense in wave theory. If light is a wave, then energy is spread continuously across the wavefront. A dim light delivers energy slowly. A bright light delivers energy quickly. But given enough time, any light should eventually deliver enough energy to knock an electron loose. The experiments say otherwise. There is also the question of timing. According to wave theory, there should be a delay. The electron should need to accumulate energy from the continuous wave before it has enough to escape. Scientists calculate that for dim light this delay should be measurable. Hours or even days for very dim sources, but there is no delay, not even a fraction of a second. The instant light of sufficient frequency hits, the metal electrons fly out, immediately, as if the energy arrives all at once rather than gradually accumulating. These results baffle physicists. They call it the photoelectric effect. They measure it precisely, they catalogue its strange properties, but they cannot explain it. Maxwell's equations, which work perfectly for so many electromagnetic phenomena, fail completely here. Something is wrong with our understanding of light, and in 1905 a 26-year-old patent clerk in Bern, Switzerland will explain exactly what. His name is Albert Einstein, and he is about to resurrect the particle theory of light from its century-long grave. Chapter 3. The Equations that Predicted the Impossible. The year is 1864. James Clerk Maxwell sits in his study at Glenlair, the family estate in Scotland. Papers cover his desk. Equations fill page after page. He's working on something that will change physics forever, but he does not know it. Yet. Maxwell is trying to understand electricity and magnetism. He wants to express the experimental discoveries of Michael Faraday in precise mathematical language. Faraday has shown that electric and magnetic fields are connected. A changing magnetic field produces an electric current. A moving electric current produces a magnetic field. The two phenomena are intertwined in ways that seem almost mystical. Maxwell believes there must be an underlying mathematical structure. Nature does not create arbitrary connections. If electricity and magnetism interact, there must be equations that describe exactly how. For years, Maxwell has been building these equations. He has used mechanical models, rotating vortices, idle wheels, strange imaginary machines that help him visualize how the fields might work. But now he is ready to abandon the models. He wants pure mathematics, elegant equations that capture the essence without the scaffolding. And he finds them. 4 equations, that is all. 4 statements about how electric and magnetic fields behave, how they are created, how they change, how they relate to each other. 4 equations that contain within them the entire science of electromagnetism. The first equation is Gauss's law for electricity. It says that electric fields flow outward from positive charges and inward toward negative charges. The strength of the field depends on the amount of charge. The second equation is Gauss's law for magnetism. It says that magnetic field lines always form closed loops. There are no magnetic monopoles, no isolated north poles, no isolated south poles. Magnetic field lines have no beginning and no end. The third equation is Faraday's law of induction. It says that a changing magnetic field creates an electric field. This is the principle behind electric generators. Spin a magnet near a wire and electricity flows. The fourth equation is Ampere's law with Maxwell's correction. It says that electric currents create magnetic fields, but Maxwell adds something new. Not just currents, but also changing electric fields. A changing electric field can create a magnetic field, just as a changing magnetic field creates an electric field. This addition is crucial. Maxwell's correction completes the symmetry. Changing electric fields create magnetic fields. Changing magnetic fields create electric fields. Each creates the other in an endless dance. And here is where the magic happens. Maxwell manipulates his equations. He combines them. He applies mathematical operations. And out falls something unexpected. A wave equation. The equations predict that disturbances in the electric and magnetic fields can propagate through empty space. An oscillating electric field creates an oscillating magnetic field, which creates an oscillating electric field, which creates an oscillating magnetic field. The disturbance sustains itself. It moves forward. It travels as a wave. What is the speed of this wave, Maxwell calculates? The answer depends on 2 physical constants: the permittivity of free space, which describes how electric fields behave in a vacuum, and the permeability of free space, which describes how magnetic fields behave in a vacuum. Both constants have been measured in laboratories. Neither has anything obviously to do with light. Maxwell plugs in the numbers. The speed comes out to about 300 million meters per second. Maxwell stares at the result. He knows this number. Everyone who studies physics knows this number. It is the speed of light, measured by astronomers observing the moons of Jupiter, measured by experimentalists in laboratories on Earth, the speed at which light crosses the universe. The agreement is too perfect to be coincidence. Maxwell understands immediately what this means. Light is not something separate from electricity and magnetism. Light is electricity and magnetism, an electromagnetic wave. In his paper of 1864, Maxwell writes words that will echo through history. This velocity is so nearly that of light that it seems we have strong reason to conclude that light itself, including radiant heat and other radiations, if any, is an electromagnetic disturbance in the form of waves propagated through the electromagnetic field according to electromagnetic laws. Think about what Maxwell has done. He started with experiments involving wires and magnets, battery circuits and compass needles, phenomena that seem to have nothing to do with light. And through pure mathematics, he discovered that light is the same thing as electricity and magnetism, 3 apparently different aspects of nature unified into one. This is one of the greatest achievements in the history of physics. Before Maxwell, there were 3 separate phenomena: electricity, magnetism, light. After Maxwell, there is only one: the electromagnetic field, a single entity that manifests in different ways depending on circumstances. But Maxwell goes further. His equations predict not just visible light but an entire spectrum of electromagnetic radiation. Waves of any wavelength should be possible, longer than red light, shorter than violet, an infinite range of invisible electromagnetic waves waiting to be discovered. The prediction is bold, revolutionary, and at first largely ignored. Maxwell dies in 1879. He is only 48 years old. Cancer claims him before he can see his greatest prediction confirmed. 8 years later, in 1887, a German physicist named Heinrich Hertz sets out to test Maxwell's theory. Hertz builds an apparatus consisting of two metal rods with a small gap between them. He connects the rods to a high voltage source. When the voltage is high enough, sparks jump across the gap. These sparks create rapid oscillations of electric current. According to Maxwell's equations, these oscillations should produce electromagnetic waves. But how can Hertz detect invisible waves? He builds a receiver. Simple loop of wire with a tiny gap. If electromagnetic waves pass through the loop, they should induce a current. The current should cause sparks to jump across the gap. Hertz places his receiver across the room from his transmitter. He turns on the voltage. Sparks jump across the transmitter gap, and sparks appear at the receiver. Electromagnetic waves have crossed the room, invisible, traveling at the speed of light, behaving exactly as Maxwell's equations predict. Hertz has discovered radio waves. Maxwell is proven right. The implications are staggering. If electromagnetic waves can travel through empty space, they can travel anywhere, across oceans, across continents, across the solar system. The universe is permeated by an electromagnetic field that can carry information at the speed of light. Within decades, radio technology transforms the world. Guglielmo Marconi sends the first transatlantic radio message in 1901. Radio broadcasts begin in the 1920s. Television follows in the 1930s. Radar helps win World War II. Communication satellites circle the Earth. Cell phones connect billions of people. All of it flows from Maxwell's equations. But there is something even more profound than technology hidden in Maxwell's work. Something that would not be fully understood until Einstein developed special relativity. Maxwell's equations make a peculiar prediction about the speed of electromagnetic waves. They say the speed is always the same, 300 million meters per second. The equations do not care about the motion of the source. They do not care about the motion of the observer. The speed of light is simply a constant, fixed, immutable, universal. This seems impossible. Ordinary speeds add and subtract. If you are on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, the ball moves at 150 kilometers per hour relative to the ground. Speeds combine, but Maxwell's equations say light does not work this way. Light always moves at the same speed, whether you are moving toward it or away from it, whether the source is approaching you or receding. The speed of light never changes. Most physicists of the late 19th century do not take this seriously. They assume Maxwell's equations are written from the perspective of the luminiferous ether, that mysterious substance supposedly filling all of space. Light waves move at 300 million meters per second relative to the ether. If you're moving through the ether, the apparent speed of light should change. Simple Newtonian mechanics. In 1887, the same year Hertz discovers radio waves, two American physicists set out to measure Earth's motion through the ether. Albert Michelson and Edward Morley build an extraordinarily precise instrument called an interferometer. It splits a beam of light, sends the two halves in perpendicular directions and recombines them. If Earth is moving through the ether, light should travel at slightly different speeds in different directions. The interference pattern should reveal the motion. The result is stunning. There is no difference. Light travels at exactly the same speed in all directions. No matter how Michelson and Morley orient their apparatus, no matter what time of year they perform the experiment, the speed of light is constant. The luminiferous ether does not exist. Or if it does, Earth is somehow always stationary relative to it. Neither explanation makes sense. This result baffles physicists for nearly 2 decades. Maxwell's equations seem to predict a constant speed of light. Experiments confirm it, but no one understands why. Then in 1905 comes Einstein. But Einstein's contribution to our understanding of light goes far beyond special relativity. In that same miraculous year of 1905, Einstein publishes another paper. This one addresses the photoelectric effect, and it resurrects an idea that has been dead for a century. Light, Einstein proposes, consists of particles, not waves. Particles, discrete packets of energy. Einstein calls them light quanta. We now call them photons. This seems to contradict everything we have just described. Young proved light is a wave. Fresnel's mathematics describe wave behavior perfectly. Maxwell showed light is an electromagnetic wave. Hertz detected electromagnetic waves. The evidence for wave nature is overwhelming, and yet the photoelectric effect cannot be explained by waves. Einstein knows this. The strange properties of light ejecting electrons from metals, the dependence on frequency, not intensity, the lack of any time delay. None of it makes sense if light is a continuous wave, but it makes perfect sense if light comes in packets. Imagine light as a stream of tiny particles, each carrying a specific amount of energy. The energy of each particle depends on its frequency. Blue light particles carry more energy than red light particles, violet more than blue, ultraviolet more than violet. When a light particle hits an electron, it delivers all its energy at once, not gradually like a wave washing over a shore, instantaneously like a billiard ball striking another ball. If the particle carries enough energy, the electron is ejected. If not, nothing happens. This explains everything. The dependence on frequency. Higher frequency means more energy per particle. Below a certain frequency, the particles simply do not carry enough energy to knock electrons loose, no matter how many of them there are. Above that frequency, electrons fly out immediately. No delay, because the energy transfer is instantaneous. Einstein even writes an equation. The energy of a light quantum equals Planck's constant times the frequency. This is the famous equation E equals h times f. It will become one of the foundations of quantum mechanics. But wait, how can light be both a wave and a particle? Waves and particles are opposites. Waves spread out, particles are localized. Waves interfere, particles collide. The concepts are mutually exclusive, or so classical physics assumes. Quantum mechanics, which is just being born in 1905, will eventually show that this assumption is wrong. Light is neither purely a wave nor purely a particle. It is something stranger, something that has no analogy in everyday experience, something that behaves as a wave when we look for wave properties, and as a particle when we look for particle properties. This is called wave-particle duality. And it is not limited to light. As we will see, matter itself, electrons, protons, neutrons, atoms, molecules, even large objects exhibit the same dual nature. The entire universe is built from entities that refuse to be either waves or particles, and somehow manage to be both. Einstein's paper on the photoelectric effect earned him the Nobel Prize in 1921. Not relativity, not the famous E equals mc squared. The Nobel Committee specifically cites his discovery of the law of the photoelectric effect, his demonstration that light consists of quanta. Maxwell's equations remain true. Light is an electromagnetic wave, but it is also composed of particles. Both descriptions are correct. Both are incomplete. Reality is stranger than either theory alone can capture. The stage is now set for the experiment that will reveal just how strange reality truly is. The experiment that Feynman called the only mystery of quantum mechanics. The experiment that shows light behaving in ways that no one can explain. The double slit experiment performed with single particles. One photon at a time. Chapter 4. Einstein's Uncomfortable Truth. Bern, Switzerland. 1905. A young man sits at a desk in the Swiss patent office. His job is to evaluate patent applications, to determine if inventions are novel and practical. It is steady work, respectable, but it is not what he truly cares about. In his spare time, between reviewing patents and during his lunch breaks, this young man thinks about physics. He thinks about time and space, about matter and energy, about light and its mysterious properties. His name is Albert Einstein. He is 26 years old, and he's about to have the most productive year in the history of physics. In 1905, Einstein publishes 4 papers in the prestigious journal Annalen der Physik. Any one of these papers would have made his reputation. Together they constitute a revolution: special relativity, the equivalence of mass and energy, the explanation of Brownian motion, and perhaps most revolutionary of all, his paper on the photoelectric effect. Einstein knows about the experimental problems with light. He knows that when ultraviolet light shines on certain metals, electrons are ejected. He knows that the properties of these ejected electrons make no sense according to classical wave theory. Let us examine these properties more carefully. First, the energy of the ejected electrons depends only on the frequency of the light, not on its intensity. Shine a dim blue light on zinc and electrons fly out at a certain speed. Shine an extremely bright red light on the same zinc and nothing happens. No electrons at all. According to wave theory, intensity should determine energy. More intense light means more energy delivered to the electrons, but that is not what experiments show. Second, there is no delay between when the light hits the metal and when electrons are ejected. Wave theory predicts that for dim light, electrons should need time to accumulate enough energy to escape. The wave delivers energy gradually. The electron absorbs it gradually. There should be a measurable delay, hours for very dim light. But there is no delay. Electrons fly out immediately, within a billionth of a second. Third, there is a threshold frequency below which no electrons are ejected regardless of intensity. Red light does not eject. Electrons from zinc, no matter how bright it is, no matter how long you shine it, the frequency is simply wrong. But increase the frequency to blue or ultraviolet, and electrons appear immediately even for dim light. Classical physics cannot explain these observations. Maxwell's electromagnetic theory describes light as a continuous wave, a wave spreading through space carrying energy distributed smoothly across its extent. Such a wave should not behave this way. Einstein proposes something radical. Light is not continuous. It comes in discrete packets, little bundles of energy. Each bundle carries an amount of energy proportional to the frequency of the light. Higher frequency means more energy per bundle. Lower frequency means less. Einstein calls these bundles like quanta. Today we call them photons. Think of it this way. A wave is like a gentle rain falling on a pond. The energy is distributed across the entire surface. Every drop is tiny. The cumulative effect builds up slowly. But photons are like hailstones. Each one carries a concentrated punch. When it hits, it delivers all its energy at once. Now the photoelectric effect makes sense. When a photon hits an electron, it transfers all its energy instantaneously. If the photon carries enough energy, the electron escapes the metal. If not, the electron stays put. The energy threshold depends on the properties of the metal. Each metal has a specific amount of energy required to release an electron. This is called the work function. Blue light photons carry more energy than red light photons. If blue photons carry more energy than the work function, electrons fly out. If red photons carry less, nothing happens. It does not matter how many red photons you send. Each one individually lacks the energy to release an electron. 1,000,000 weak punches cannot equal one strong one. This explains the frequency dependence. Only photons above the threshold frequency carry enough energy. The number of photons determines how many electrons are released. But the energy of each photon determines whether any electrons are released at all. The lack of delay is also explained. Energy transfer is instantaneous. One photon hits one electron. Bang! The electron flies out or it does not. No gradual accumulation, no waiting. The process is immediate because it involves discrete interactions, not continuous absorption. Einstein's equation is elegant and precise. The maximum kinetic energy of an ejected electron equals the photon energy minus the work function. Written as an equation, the maximum kinetic energy equals Planck's constant times the frequency minus the work function of the metal. Planck's constant appears in the equation. This is not a coincidence. 5 years earlier, in 1900, the German physicist Max Planck had introduced this constant in his explanation of blackbody radiation. Planck showed that heated objects emit light in discrete amounts, not in a continuous spectrum. The energy of each quantum is proportional to the frequency with Planck's constant as the proportionality factor. Planck himself did not fully believe in quanta. He considered his solution a mathematical trick, a calculational device that happened to give the right answer. He did not think light actually came in discrete packets. Einstein takes Planck's idea seriously. He proposes that light quanta are real physical entities, not a mathematical convenience, but an actual description of how light exists. This is an audacious claim. It directly contradicts a century of accumulated evidence that light is a wave. Young's interference experiments, Fresnel's diffraction calculations, Maxwell's electromagnetic theory, all of it points to waves, continuous waves spreading through space and interfering with each other, and yet the photoelectric effect demands particles. Einstein is aware of the contradiction. In his paper, he describes his hypothesis as heuristic, a useful point of view that explains certain phenomena. He is not claiming that light is only particles. He is suggesting that in some circumstances light behaves as if it consists of discrete quanta. The physics community is skeptical. Robert Millikan, an American physicist, sets out to disprove Einstein's hypothesis. For 10 years, Millikan conducts precise experiments on the photoelectric effect. He measures the energy of ejected electrons with extreme accuracy. He varies the frequency and intensity of light systematically, and he confirms Einstein's equation exactly. Every prediction Einstein makes is correct. The relationship between photon energy and frequency, the existence of a threshold frequency, the immediate ejection with no time delay. Millikan's experiments in 1914 verify it all. Ironically, Millikan remains unconvinced. He writes that his experiments prove Einstein's equation correct, while simultaneously calling Einstein's interpretation of that equation radical hypothesis and unthinkable. Even after proving Einstein right, Millikan cannot accept that light comes in particles. But the evidence is overwhelming. The physics community gradually accepts that light has a dual nature. It behaves as a wave in some experiments and as a particle in others. Both descriptions are necessary, neither alone is complete. Einstein wins the Nobel Prize in Physics in 1921. The citation specifically mentions his discovery of the law of the photoelectric effect, not relativity, not E equals mc squared. The Nobel Committee explicitly honors his work on light quanta. But Einstein himself is troubled by what he has unleashed. The quantum theory that grows from his insight will become stranger and more counterintuitive with each passing year. Particles that exist in multiple places simultaneously, measurements that seem to affect distant objects instantaneously, a probabilistic universe where outcomes cannot be predicted, only described statistically. Einstein will spend the last 3 decades of his life arguing against these implications. He will famously declare that God does not play dice with the universe. He will propose thought experiments designed to reveal contradictions in quantum mechanics. He will correspond with Niels Bohr debating the foundations of the theory he helped create, and he will never be satisfied with quantum mechanics. Despite its stunning experimental success, Einstein will go to his grave believing that something deeper lies beneath, some hidden reality that quantum mechanics describes only approximately. Was Einstein right? Are there hidden variables underlying quantum mechanics? Experiments in the 1980s and beyond seem to say no. The universe appears to be fundamentally probabilistic. The strangeness is not an artifact of incomplete knowledge, it is built into the fabric of reality. But we are getting ahead of ourselves. In 1905, Einstein has established that light consists of particles. Young and Maxwell established that light is a wave. Both are correct. Light is somehow both. The full implications of this duality will not become clear for another 2 decades. In the 1920s, a new generation of physicists will develop quantum mechanics. Werner Heisenberg, Max Born, Pascal Jordan, and Erwin Schrödinger will create mathematical frameworks that describe the quantum world. Niels Bohr will articulate the Copenhagen interpretation, and the double-slit experiment will be refined to reveal just how strange wave-particle duality really is. Because here is the thing. When Young performed his experiment in 1801, he used beams of light, many billions of photons passing through the slits simultaneously. The interference pattern he observed could be explained as waves interacting, many waves superimposing and creating bright and dark bands. But what happens if you send only one photon at a time? What happens if you ensure that there is never more than one particle passing through the apparatus? What happens if you fire photons one by one, waiting for each to arrive before sending the next? According to classical intuition, the answer is obvious. A single particle goes through one slit or the other. It cannot interfere with itself. There is no other particle to interfere with. The pattern on the screen should simply be 2 bands corresponding to the 2 slits. Particle behavior. But that is not what happens. Even single photons fired one at a time build up an interference pattern. Over time, as thousands of individual photons hit the screen, They gradually form the same pattern of bright and dark bands that Young observed. Each photon is a particle. Each one arrives at a single point on the screen, and yet somehow collectively they form a wave pattern. It gets stranger. Each individual photon seems to go through both slits simultaneously. How do we know this? Because if we block one slit, the interference pattern disappears. The pattern requires both slits to be open, but a particle can only go through one slit. So how can blocking one slit affect a particle that supposedly went through the other? The mathematics of quantum mechanics provides an answer. Sort of. The photon does not really go through one slit or the other. It exists in what is called a superposition of states, a quantum combination of going through the left slit and going through the right slit. Only when the photon hits the screen does this superposition collapse into a definite outcome, a single point of impact. This is the measurement problem. The act of measurement seems to change the system. Before measurement, the photon is a wave spread across space, potentially going through both slits. After measurement, it is a particle located at one specific point. The transition from wave to particle, from superposition to definite outcome, remains one of the deepest mysteries in physics, and it is about to get even more mysterious. Because when we try to observe which slit the photon goes through, something remarkable happens. The interference pattern disappears. The mere act of observation changes the behavior of light. We will explore this phenomenon in the next chapter, the observer effect, the curse of knowing. The experiment that suggests reality itself depends on whether anyone is watching. Chapter 5. The experiment that broke reality. Imagine a laboratory. Clean, sterile, quiet. The equipment is simple. A source that can emit single photons one at a time. A barrier with two narrow slits. A detector screen that records where each photon lands. This is the double-slit experiment. The same experiment Thomas Young performed in 1801, but with one crucial difference. We are not using a beam of light. We are not sending billions of photons through the slits simultaneously. We are sending one photon at a time. One. Then we wait. Then another. Then we wait. Photon by photon, we build up a picture of how light behaves. The first photon is released. It travels toward the slits. It passes through. It hits the screen. A single dot appears. One tiny flash of light at one specific location. Nothing surprising so far. A particle behaving like a particle. Going somewhere. Arriving somewhere. Making a mark. The second photon is released. Another dot appears on the screen. A different location. Still nothing strange. We continue. 10 photons. 100. 1,000. The dots accumulate, and a pattern begins to emerge. Not the pattern you would expect. Not two bright strips corresponding to the two slits. Not the pattern of particles passing through one opening or the other. Instead, an interference pattern. Bright bands where many dots cluster together, dark bands where almost no dots appear, alternating light and dark across the screen. The same pattern Young saw, the same pattern that proved light as a wave. But we sent particles, one at a time. Each photon arrived as a single dot, each one behaved like a particle when it hit the screen, and yet collectively they form a wave pattern. How is this possible? How can particles that arrive one at a time interfere with each other? They never coexist. When one photon hits the screen, the next has not yet been emitted. There is nothing to interfere with, unless each photon interferes with itself. This sounds absurd. A single particle dividing into two parts, passing through both slits simultaneously, and then recombining to create interference. Particles do not do this. Particles go through one path or another. They do not split into multiple versions of themselves, and yet the experimental evidence is undeniable. If we block one slit, the interference pattern disappears. The remaining pattern is just a bright band corresponding to the open slit. Normal particle behavior. This proves that both slits must be involved in creating the interference pattern, but each photon is a single indivisible quantum. It cannot actually split in half. So how can it pass through both slits? Quantum mechanics provides a mathematical description. The photon is described by a wave function, a mathematical object that spreads through space like a wave. This wave function passes through both slits. It interferes with itself, and when the photon is detected, the wave function collapses to a single point. The wave function does not tell us where the photon is, it tells us where the photon might be. The probability of finding the photon at any given location is proportional to the square of the wave function at that location. Where the wave function is large, the photon is likely to appear. Where it is small, the photon rarely appears. Where it is zero, due to destructive interference, the photon never appears. This is why the dark bands exist. The wave function passing through both slits interferes destructively at certain angles. The probability of detecting a photon there is zero, even though a straight line from the source. Through either slit passes through these dark regions, photons never land there. Each photon seems to know about both slits. Each one behaves as if it travelled through both paths simultaneously. And yet when we detect it, we find a single particle at a single location. Richard Feynman called this the only mystery of quantum mechanics. He did not mean that quantum mechanics has only one strange phenomenon. He meant that if you truly understand the double-slit experiment, you understand the heart of quantum weirdness. And if you do not understand this experiment, you do not understand quantum mechanics at all. Let us make the mystery more concrete. Picture a single photon approaching the double slit. According to classical intuition, the photon must go through one slit or the other. Let us say it goes through the left slit. Then it should behave as if only the left slit exists. It should not care about the right slit at all. But this prediction is wrong. The interference pattern proves that both slits matter. Even for a single photon, blocking either slit changes the pattern entirely. Now picture the same photon in quantum mechanical terms. It is not a tiny ball travelling along a definite path. It is a wave function spreading through space. This wave function encounters the barrier. Part of it passes through the left slit. Part of it passes through the right slit. The two parts spread out beyond the barrier and overlap. Where they overlap, they interfere. When the photon is detected, the wave function collapses. The photon appears at one location. But the probability of appearing at any given location was shaped by the interference of both paths. The photon did not go through the left slit. It did not go through the right slit. It went through both, and neither. The question itself assumes a classical reality that does not apply. In quantum mechanics, asking which slit the photon went through may have no definite answer. This is deeply unsettling. We are accustomed to thinking that things have definite properties. A ball is either in the left box or the right box. A cat is either alive or dead. An electron is either here or there. Classical physics is built on this assumption. Quantum mechanics says the assumption is wrong. At the fundamental level, particles do not have definite positions until they are measured. They exist in superpositions of different possibilities. The act of measurement forces a choice, collapses the superposition into a definite outcome, creates the reality we observe. But what counts as a measurement? Who or what is the observer? Does the universe really wait for someone to look before deciding what happens? These questions have been debated for nearly a century. They remain unresolved. Let us perform a thought experiment. Suppose we want to know which slit each photon goes through. We set up a detector at one of the slits. Every time a photon passes through that slit, our detector clicks. If the detector does not click, the photon must have gone through the other slit. Now we run the experiment again. Photon after photon. Each time our detector tells us which slit was used. We record both the slit and the landing position on the screen. What pattern do we see? The interference pattern is gone. Instead of alternating bright and dark bands, we see two overlapping blobs. Just what you would expect from particles passing through one slit or the other. No interference, no wave behavior, just particles being particles. The mere act of observing which slit the photon passes through destroys the interference. The act of measurement changes the outcome. This is not because our detector physically disturbs the photon. Physicists have devised increasingly clever experiments to measure the path with minimal physical interaction. It does not matter. Any method of determining which slit the photon passed through eliminates the interference pattern. It is as if the photon knows whether anyone is watching. When unobserved, it behaves as a wave passing through both slits, interfering with itself, creating patterns of probability. When observed, it behaves as a particle passing through one slit, travelling in a straight line, behaving classically. This is the observer effect, the apparent influence of observation on quantum systems, the seeming dependence of reality on whether anyone is looking. Before we go further, we should address a common misconception. The observer in quantum mechanics is not necessarily a conscious human being. The observer effect does not require a mind. What matters is whether information about the photon's path exists in the physical world, whether that information is recorded in a detector in a memory bank in the state of other particles. If the which path information is recorded anywhere, the interference pattern disappears. The photon behaves as a particle. If the information is not recorded, if there is no physical record of which slit was used, the photon behaves as a wave. Interference remains, consciousness is not required. But information is. This leads to one of the strangest experiments in physics, the quantum eraser. In this experiment, we use a clever setup to record the which path information and then erase it. If the information is truly erased with no physical record remaining, can the interference pattern be restored? The answer is yes. If we record which slit each photon passes through, and then destroy that information before looking at the final results, the interference pattern reappears. It is as if the photons knew that the information would eventually be erased. They interfered despite being monitored, because the monitoring would ultimately leave no trace. This raises profound questions about the nature of information in quantum mechanics. Information seems to play a fundamental role, perhaps more fundamental than matter or energy. The universe seems to track what information exists and to adjust physical outcomes accordingly. We will explore these ideas further in later chapters. The quantum eraser leads to even stranger variations. The delayed choice quantum eraser suggests that actions in the future might affect events in the past. These experiments push the boundaries of causality itself. But for now, let us pause and reflect on what the double slit experiment tells us about light. Light is not simply a wave. Light is not simply a particle. Light is something else entirely. Something that our language and intuition are not equipped to describe. Something that behaves differently depending on how we interact with it. The double slit experiment does not merely demonstrate wave-particle duality. It demonstrates that the universe, at its most fundamental level, operates according to rules that make no classical sense. Particles can be in two places at once. Observation affects outcomes. Information determines physical behavior. These are not metaphors. They are not interpretations. They are experimental facts, reproduced countless times in laboratories around the world, not just with light, but with electrons, with neutrons, with atoms, even with molecules containing thousands of atoms. Wave-particle duality is a universal feature of reality. What does it mean? After nearly a century of quantum mechanics, physicists still disagree. The Copenhagen interpretation says we should not ask what is really happening. The wave function is a tool for calculating probabilities, not a description of physical reality. The many worlds interpretation says every possible outcome actually occurs in parallel universes. The wave function never collapses. It just looks that way from within a particular branch of the multiverse. Other interpretations exist: pilot wave theory, relational quantum mechanics, cubism. Each offers a different picture of what the mathematics means. None can be distinguished experimentally. The quantum formalism is perfectly consistent, but its interpretation remains open. Einstein never accepted the Copenhagen interpretation. He believed that quantum mechanics was incomplete, that there must be hidden variables determining outcomes that we simply cannot access. He famously collaborated with Boris Podolsky and Nathan Rosen to devise a thought experiment meant to reveal the incompleteness of quantum mechanics. That thought experiment involves something Einstein called spooky action at a distance, quantum entanglement, and it is where we turn next. Chapter 6: The Observer's Curse. The year is 1998. At the Weizmann Institute of Science in Israel, a team of physicists led by Mordechai Heiblum conducts an experiment that will send ripples through the foundations of physics. They are not using photons, they are using electrons, but the principle is the same, and the results are equally disturbing. The team builds a tiny device smaller than a human hair. It contains a barrier with two openings. Electrons flow through these openings and create an interference pattern on the other side. Wave behavior, just like the double slit experiment with light. Then they add something new, a detector, a tiny electronic sensor placed near one of the openings. This detector can observe which path each electron takes. It can register whether an electron passes through the left opening or the right opening. The detector does not physically block anything. It does not touch the electrons. It simply watches. It simply records. And the interference pattern vanishes. When the detector is turned off, the interference pattern returns. Electrons behave as waves. They pass through both openings simultaneously. They interfere with themselves. Bright and dark bands appear. When the detector is turned on, the interference pattern disappears. Electrons behave as particles. Each one goes through one opening or the other. No interference. just two overlapping blobs. The team goes further. They vary the sensitivity of their detector. They make it more or less capable of observing the electrons, and they find a smooth transition. The more effectively the detector observes the electrons, the more the interference pattern fades. Partial observation leads to partial interference. Complete observation eliminates interference entirely. The act of observation changes physical reality. This is the observer effect in its purest form, not a philosophical speculation, not a thought experiment, a real measurable phenomenon demonstrated in a laboratory with precise instruments and careful controls. But what exactly is happening? Why should observation matter? The electrons do not care about human scientists. They do not know they are being watched. So why does the presence of a detector change their behavior? The answer lies in the nature of information. When an electron passes through one opening or the other without being observed, no information about its path exists in the universe. The electron is truly in a superposition, a quantum combination of both paths. The wave function includes both possibilities and they interfere. When a detector observes, the electron information is created. The detector enters a different state depending on which path the electron took. This information now exists in the physical world. It is encoded in the detector, and this encoding is what destroys the interference. The electron becomes entangled with the detector. Their quantum states become correlated, and once entangled, the electron can no longer interfere with itself. The superposition has effectively collapsed, not because anyone looked at the detector, simply because the information exists. This is subtle and counterintuitive. Let us think about it more carefully. In classical physics, information is passive. Whether you know something or not does not change what is true. The moon exists whether you look at it or not. A coin is either heads or tails whether you check or not. Information describes reality but does not shape it. In quantum mechanics, this is not true. Information and reality are intertwined. The existence of information about a quantum system changes how that system behaves. Not metaphorically, physically, measurably. Consider the delayed choice experiment proposed by John Wheeler in 1978. Wheeler imagined light from a distant quasar travelling toward Earth. The light passes near a galaxy whose gravity bends space. Because of this bending, the light can reach Earth by two different paths, one going around the left side of the galaxy, one going around the right side. This is a cosmic double slit experiment. The galaxy is the barrier. The two paths around it are the slits. The Earth is the detector screen. Wheeler asks a strange question. What if we choose how to observe the light after it has already passed the galaxy? After it has already taken its path or paths through space? We could set up a detector that measures which path the light took. In this case, we expect to see particle behavior. Light that took the left path, light that took the right path. No interference. Or we could set up an interferometer that combines both paths and looks for interference. In this case, we expect to see wave behavior, an interference pattern revealing that light took both paths simultaneously. The choice is ours. We can make it after the light has been travelling for billions of years, after it has already passed the galaxy, after whatever happened has already happened. And yet our choice matters. If we choose to measure which path the light takes, we find that each photon took one path, a definite trajectory, particle behavior. If we choose to look for interference, we find an interference pattern. The photons took both paths, wave behavior. This seems to imply that our choice now affects what happened billions of years ago, that our observation retroactively determines whether the photon was a wave or a particle when it passed the galaxy. Wheeler does not believe in backwards causation. He interprets the experiment differently. He says that until the photon is detected, there is no fact of the matter about which path it took. The question is meaningless. The photon does not have a definite history until that history is observed. This is the Copenhagen interpretation in its strongest form. The past is not fixed until it is recorded. History is created by observation. Reality crystallizes out of possibility only when information about it comes into existence. Einstein would have hated this. He believed in an objective reality independent of observers. He believed the moon exists whether anyone looks at it. He believed that particles have definite properties whether those properties are measured or not. Einstein and Bohr debated these issues for decades. Their arguments are legendary. The Bohr-Einstein debates shaped the development of quantum mechanics and defined the philosophical battleground that physicists still fight over today. In 1935, Einstein, with two colleagues Boris Podolsky and Nathan Rosen, published a paper meant to expose the absurdity of quantum mechanics. The paper described what is now called the EPR paradox, named after the three authors. The argument goes like this: quantum mechanics allows for entangled particles, two particles whose properties are correlated. If you measure one particle, you instantly know something about the other, no matter how far apart they are. Consider two electrons created together in such a way that their spins are opposite. If one is spin up, the other is spin down. They fly apart, travelling to opposite sides of the universe. Neither has a definite spin until measured. Both are in superposition. Now measure one of them, say it is spin up. Instantly the other becomes spin down. The measurement on one particle seems to affect the other particle instantaneously, across any distance. Einstein called this spooky action at a distance. He argued that it violated special relativity, which forbids information from travelling faster than light. How can a measurement here instantly change a particle there? His conclusion was that quantum mechanics must be incomplete. There must be hidden variables that determine the spins from the beginning. The particles only appear random because we do not know these hidden variables. In reality, everything is determined. The apparent spookiness is just our ignorance. For decades, this seemed like a philosophical debate impossible to resolve experimentally. But in 1964, a physicist named John Bell showed that Einstein was testable. Bell derived an inequality, a mathematical limit on how correlated measurement results can be if hidden variables exist. If quantum mechanics is correct, and there are no hidden variables, then experiments should violate Bell's inequality. If Einstein is right and hidden variables exist, then Bell's inequality should hold. Experiments began in the 1970s and have continued ever since. The results are unambiguous. Bell's inequality is violated. Quantum mechanics is correct. Einstein was wrong about hidden variables. This does not mean information travels faster than light. The correlations between entangled particles cannot be used to send messages. When you measure one particle, you get a random result. You cannot control whether it is spin up or spin down. You cannot encode information. The correlation only becomes apparent when you compare both measurements, and that comparison requires classical communication. But the correlations are real, and they cannot be explained by hidden variables. The universe is fundamentally random at the quantum level. Outcomes are not determined until they are measured. Einstein's dream of an underlying deterministic reality does not match experimental facts. This has profound implications for the observer effect. If particles do not have definite properties until measured, then observation does not merely reveal reality. Observation creates reality. The act of measurement brings into existence properties that did not exist before. What is the observer then? What counts as a measurement? Does the universe care about human consciousness or only about physical interactions? The answers are controversial. The Copenhagen interpretation says measurements occur when quantum systems interact with classical measuring devices. But all devices are ultimately made of quantum particles. Where is the boundary between quantum and classical? No one knows. The many worlds interpretation says there is no collapse. All possible outcomes occur. The observer becomes entangled with the system and experiences only one branch of the resulting superposition. From the inside, it looks like collapse, but nothing actually collapses. Decoherence theory explains how quantum superpositions become effectively classical through interaction with the environment. A particle does not need a conscious observer. It just needs to interact with enough other particles. Information about its state spreads into the environment and interference is destroyed. Each interpretation has its advocates. None can be tested experimentally. The mathematics of quantum mechanics is precise and predictive. But what the mathematics means is still debated. One thing is clear. The observer, whether human or machine or environment, plays a role in quantum mechanics that has no analogue in classical physics. Observation matters. Information matters. The act of recording which path a particle takes changes the physics of that particle. This is the observer's curse. The more we look, the less we see. The more we try to pin down quantum reality, the more it slips away. Light reveals itself as particles when we look for particles, and waves when we look for waves. But it never reveals both at once. It never lets us see behind the curtain. Perhaps there is nothing behind the curtain. Perhaps the wave function is all there is. Perhaps asking what is really happening when no one looks is asking a meaningless question. Or perhaps we simply do not yet have the concepts to understand what is really happening. Perhaps some future physics will make sense of quantum mechanics just as relativity made sense of electromagnetism. Perhaps the mystery will one day be solved. For now, the observer's curse remains. Watch a particle, and you change it. Try to know which path it took, and you destroy the interference. Seek certainty, and you find uncertainty. The universe keeps its secrets, and the deepest secrets involve not single particles, but pairs, entangled particles that seem to communicate instantaneously across space. Einstein's spooky action at a distance. That is where we turn next. Chapter 7. Spooky action at a distance. Imagine two photons born together in the same instant, created from a single event. A crystal splits one photon of high energy into two photons of lower energy. The two photons fly apart in opposite directions. One goes left, one goes right. They travel at the speed of light, separating by millions of kilometers every second. These photons are entangled. Their properties are correlated in a way that has no classical explanation. Neither photon has a definite polarization until measured, but when one is measured, the other instantly acquires the opposite polarization. Instantly, regardless of distance. This is quantum entanglement. The phenomenon that Einstein called spooky action at a distance. The connection that seems to violate everything we know about locality and causality. The mystery that has confounded physicists for nearly a century. Let us set up an experiment. Alice is on Earth. Bob is on Mars. A source located between them creates entangled photon pairs and sends one photon to each of them. Alice and Bob each have a polarization detector. They can measure whether their photon is polarized vertically or horizontally. The photons are created in what is called a Bell state, a quantum superposition where both photons have the same polarization, but neither has a definite polarization until measured. If Alice measures vertical, she will get a random result. 50% of the time vertical, 50% of the time horizontal. But here is the strange part. Whatever result Alice gets, Bob gets the same. If Alice measures vertical and gets vertical, then Bob measures vertical and gets vertical. If Alice gets horizontal, then Bob gets horizontal. The results are perfectly correlated. The correlation is instantaneous. When Alice measures her photon on Earth, the result of Bob's measurement on Mars is immediately determined. Mars is about 3 light minutes from Earth on average, but the correlation does not wait 3 minutes to propagate, it is immediate. Does this mean information travels faster than light? Can Alice send a message to Bob instantaneously? No. And this is crucial. Alice cannot control what result she gets. She cannot choose to measure vertical and get vertical. The outcome is random. She has no way to encode information in her measurement. Bob sees only random results on his end. It is only when Alice and Bob compare their measurements, later using ordinary communication, that the correlation becomes apparent. So entanglement does not violate special relativity. No information travels faster than light, but something travels faster than light. Or rather, something is correlated faster than light. The correlation exists. It is real. It just cannot be used for communication. Einstein found this deeply troubling. In 1935, he and his colleagues Podolsky and Rosen published their famous EPR paper arguing that quantum mechanics must be incomplete. Their argument was clever and seemingly airtight. They reasoned as follows. When Alice measures her photon and gets a definite result, Bob's photon must also acquire a definite polarization, instantly, regardless of distance, but according to special relativity, nothing can influence a distant object faster than light. Therefore, Bob's photon must have had a definite polarization all along. It just appeared random because we did not know the hidden variable that determined it. If hidden variables exist, then quantum mechanics is incomplete. The wave function does not tell the whole story. There is some deeper reality underlying the quantum description. The apparent randomness is just ignorance of this deeper level. This seemed like a philosophical debate impossible to settle experimentally. Both views predicted the same correlations. How could anyone tell whether the correlations came from hidden variables or from genuine spooky action? In 1964, John Bell found a way. Bell was a physicist working at CERN. He was dissatisfied with the Copenhagen interpretation and wanted to take the EPR argument seriously. Could hidden variables really explain quantum mechanics? Bell set out to answer this question. mathematically. What Bell discovered surprised him. Hidden variables do make predictions, and those predictions differ from quantum mechanics, not for the simple case Einstein considered, but for a more general situation. Instead of measuring polarization along the same axis, Alice and Bob can measure along different axes. They can choose their axis randomly for each measurement. Sometimes Alice measures vertical while Bob measures at 45 degrees. Sometimes Alice measures at 30 degrees while Bob measures horizontal. The possibilities are endless. For any given pair of measurements, quantum mechanics predicts specific correlations. These correlations depend on the angle between Alice's axis and Bob's axis. When the axes are the same, the correlation is perfect. When the axes are perpendicular, the correlation is zero. In between, the correlation varies smoothly. Bell showed that if hidden variables exist, there is a limit to how strong the correlations can be. This limit is now called Bell's inequality. Any theory with local hidden variables must satisfy this inequality. It is a mathematical theorem, and quantum mechanics violates it. According to quantum mechanics, the correlations between entangled particles can be stronger than any local hidden variable theory allows. The difference is measurable. An experiment can distinguish between quantum mechanics and local hidden variables. This was a breakthrough. Finally, the philosophical debate could be settled in the laboratory. The experiments began in the 1970s. Alain Aspect in France, John Clauser in the United States, and others built increasingly sophisticated apparatus to test Bell's inequality. They created entangled photon pairs. They measured polarizations along randomly chosen axes. They compared results. The verdict was clear. Bell's inequality was violated. Quantum mechanics was right. Local hidden variables were ruled out. But the experiments had loopholes. Critics pointed out that maybe the detectors were not efficient enough. Maybe some photons were missed and the statistics were skewed. Maybe the choice of measurement axis was not truly random. Maybe information somehow leaked between the detectors. Over the decades, experimentalists closed these loopholes one by one. Better detectors, true random number generators, measurements made so quickly that no signal even traveling at light speed could connect them. In 2015, 3 experiments simultaneously closed all known loopholes. The results were unambiguous. Bell's inequality is violated. The universe is not locally realistic. Einstein was wrong. What does not locally realistic mean? It means at least one of two things must be false. Either locality, the principle that distant events cannot instantly influence each other, or realism, the principle that particles have definite properties before measurement. Most physicists give up realism. They accept that particles do not have definite properties until measured. The wave function is not merely a description of our ignorance, it is a complete description of physical reality. There are no hidden variables. But some physicists give up locality instead. They propose that entanglement involves some kind of non-local connection between particles, not a signal travelling through space, but some deeper link in the fabric of reality, a connection that exists outside of space and time. Neither option is comfortable. Both challenge our basic intuitions about how the universe works, but the experiments force us to choose. In 2017, Chinese scientists demonstrated entanglement over a distance of more than 1,200 kilometers. They used a satellite to distribute entangled photons between ground stations in different provinces of China. The correlations held. Bell's inequality was violated at a distance greater than any previous experiment. In 2023, experiments at the Large Hadron Collider demonstrated entanglement between top quarks, the heaviest known fundamental particles so massive they exist for only a trillionth of a second before decaying. Even these ephemeral giants show quantum entanglement. Spooky action at a distance persists at the highest energies ever probed. What does all this mean for light? Photons are the particles we most often use to demonstrate entanglement. They are easy to create, easy to manipulate, easy to detect. Every major entanglement experiment uses photons, but entanglement reveals something about light that goes beyond wave-particle duality. It reveals that photons can be connected to each other in ways that transcend space, that measuring one photon can instantly determine the state of another photon arbitrarily far away, that the separateness we perceive between objects may be an illusion. Some physicists speculate that entanglement is the glue that holds space-time together, that the geometry of space itself emerges from the entanglement structure of quantum fields. This is speculative and unproven, but it suggests that the connections between photons may be more fundamental than the space those photons travel through. Einstein never accepted quantum entanglement as a real phenomenon. He went to his grave believing that there must be a deeper explanation, a hidden layer of reality that would restore common sense to physics. But the experiments have spoken. There is no hidden layer, no deeper explanation in terms of local hidden variables. The universe really is that strange. Particles really are connected across distances in ways that cannot be explained by anything travelling through space. Spooky action at a distance is real. Einstein was right to be disturbed by it, but he was wrong to think it could be explained away, and the strangeness does not end with entanglement. There is an experiment that takes these ideas even further, an experiment that seems to show the future affecting the past. An experiment that challenges our most basic notions of time and causality. The delayed choice quantum eraser. That is where we turn next. Chapter 8. When Tomorrow Changes Yesterday. The experiment we are about to describe is one of the strangest ever performed. It seems to suggest that the future can reach back and alter the past, that choices made after an event can change what happened before, that causality itself can run backwards. This is the delayed choice quantum eraser. First proposed in the early 1980s, first performed in the late 1990s, replicated and refined many times since. The results are consistent and undeniable. Their interpretation remains controversial. Let us build up to the experiment step by step. Start with the ordinary double slit experiment. A photon approaches two slits. It passes through, both simultaneously existing in superposition. It lands on a detector screen. When we repeat this many times, an interference pattern emerges. Wave behavior. Now add a witch path detector, a device that records which slit each photon passes through. Immediately the interference pattern vanishes. The photons behave as particles. Knowing the path destroys the interference. So far, so familiar. This is the observer effect we discussed earlier. Information about which slit destroys the wave behavior. Now for the twist. What if we could erase the witch path information after recording it? What if we could delete the knowledge of which slit the photon took? Would the interference pattern return? The answer is yes. This is the quantum eraser. Here is how it works. Instead of directly detecting which slit each photon goes through, we use a more subtle method. We pass each photon through a special crystal that converts it into two entangled photons. One photon, called the signal photon, continues toward the detector screen. The other photon, called the idler photon, goes off in a different direction. The idler photon carries information about which slit the original photon went through. By measuring the idler photon, we can in principle determine the path of the signal photon. This is equivalent to placing a detector at the slits. The witch path information exists, and as expected, the signal photons show no interference pattern, just a blob, particle behavior. But now we add something clever. We give the idler photons two possible paths to take after being created. One path leads to a detector that preserves the witch path information. The other path leads to a detector that erases it. The erasure is accomplished using beam splitters and mirrors. The idler photon from slit A and the idler photon from slit B are combined in such a way that we cannot tell which is which. The information about the original path is destroyed. It no longer exists anywhere in the universe. When we look at signal photons whose idlers were erased, the interference pattern reappears. When we look at signal photons whose idlers were not erased, no interference. The erased photons show wave behavior. The unerased photons show particle behavior. This alone is remarkable. We can restore interference by erasing information about a different photon somewhere else in the apparatus. The signal photon and idler photon can be far apart. The erasure of information about the idler photon changes the pattern formed by the signal photon. But the delayed choice version is stranger still. In the delayed choice quantum eraser, we arrange the experiment so that the signal photon reaches its detector before the idler photon reaches its detector. The signal photon arrives, it is recorded, it has already made its mark on the screen, and then afterwards the idler photon is either erased or not. The decision about whether to erase happens after the signal photon has already been detected. The signal photon has already behaved as a wave or a particle. It has already landed somewhere, and yet the erasure of the idler photon after the fact determines whether the signal photon shows interference. Let that sink in. The signal photon has already arrived. Its position is fixed. It cannot move. and yet somehow a measurement made later on a different photon determines whether it was part of an interference pattern or not. Does this mean the future affects the past? The standard interpretation says no. The interference pattern only becomes visible when we sort the signal photons according to what happened to their idlers. Looking at all signal photons together, we see no pattern, just a blob. The interference is hidden in subsets of the data. When we later record which idler photons were erased, we can go back and separate the signal photons into two groups. Those whose idlers were erased show interference. Those whose idlers were not erased show no interference. The two patterns overlap perfectly to create the overall blob, so no information travels backward in time. No message can be sent from the future to the past. The results only become meaningful when we combine data from both detectors, and that combination requires ordinary forward-in-time communication. But the situation is still deeply strange. At the moment the signal photon hits the detector, it has already been determined whether it will be part of the interference pattern or not. That determination depends on what will happen to the idler photon in the future. The correlation between signal and idler exists outside of time. Some physicists interpret this as evidence that the past is not fixed until the future is determined, that history is not written until it is observed, that causality can flow backwards as well as forwards. Others interpret it more conservatively. The correlation is just entanglement. Nothing special happens in time. The strangeness is in our classical intuitions, not in the physics. John Wheeler, who proposed the original delayed choice thought experiment, offered an evocative image. He imagined light from distant quasars travelling for billions of years before reaching Earth. We can choose now to measure that light as waves or particles, and our choice seems to retroactively determine how the light behaved billions of years ago. Wheeler called this the participatory universe. The past has no definite reality until observers in the present make measurements. We are not passive observers reading a pre-existing history. We are participants creating history through our observations. This is a radical view. Most physicists do not fully embrace it. But no one can deny the experimental facts. The delayed choice quantum eraser works as described. The correlations are real. The mathematics of quantum mechanics predicts exactly what is observed. What does this tell us about light? It tells us that photons exist in a realm where our ordinary concepts of time and causality break down, where information seems to flow in impossible directions, where the boundaries between past and future become blurred. A photon does not have a definite history until that history is measured. The question of which slit it went through has no answer until information about that path is recorded or erased, and whether we record or erase that information can be decided after the photon has finished its journey. This is not science fiction. This is established experimental physics, performed in laboratories around the world, confirming the predictions of quantum mechanics with exquisite precision. The delayed choice quantum eraser does not allow time travel or faster-than-light communication. It does not violate any known laws of physics, but it reveals that those laws operate in ways far stranger than we ever imagined. Light remembers what we will choose to forget. It forgets what we will choose to remember, and it does all this before we make our choice. The universe is not a stage on which events play out. It is a tapestry being woven from threads that run in all directions. Past and future are not separate. They are entangled like the photons in our experiments. Each depends on the other. Neither is complete without the other. This is the deepest mystery of light. Not just wave-particle duality, not just the observer effect, not just entanglement, but the collapse of our ordinary sense of time, the dissolution of the barrier between what was and what will be. We have travelled far from Thomas Young's darkened room in 1801, from sunlight passing through two slits and making patterns on a screen. We have journeyed through Maxwell's equations and Einstein's photons, through quantum mechanics and Bell's theorem, through entanglement and erasure, and we have arrived at a place where our language fails, where our concepts bend and break, where the only honest response is wonder. But our journey is not yet complete. There are phenomena involving light that remain genuinely unexplained, mysteries that quantum mechanics itself cannot solve. In the next chapter, we will explore one of the strangest of these, a phenomenon where sound becomes light, where bubbles generate temperatures hotter than the surface of the sun, where physics admits it simply does not know what is happening. Sonoluminescence, sound into light. Chapter 9. Sound into Light. The year is 1934. At the University of Cologne in Germany, two physicists are working with ultrasound equipment. They are passing high-frequency sound waves through water, trying to understand how the waves interact with the liquid. They are not looking for light. They are not expecting light. But light is what they find. The water begins to glow. Faint blue light emanates from the liquid wherever the sound waves pass through it. The glow is dim, barely visible in a darkened room, but it is unmistakably there. Sound waves somehow creating light. The physicists publish their observation, but they cannot explain it. They call the phenomenon sonoluminescence, light from sound, and for the next 60 years it remains one of the strangest unsolved puzzles in physics. The mystery deepens when scientists examine what is happening more closely. The glow is not coming from the water itself. It is coming from tiny bubbles. The sound waves cause microscopic bubbles to form in the liquid. These bubbles grow and then collapse violently. And in the moment of collapse, they emit light. This process is called acoustic cavitation. The sound waves create alternating regions of high and low pressure in the liquid. During the low pressure phase, dissolved gases come out of solution forming tiny bubbles. During the high pressure phase, these bubbles are crushed. They collapse inward at incredible speed. And somehow this collapse produces light. For decades, this was all scientists knew. Many bubbles formed and collapsed chaotically. The light was weak and difficult to study. The phenomenon seemed more curiosity than physics. Then in 1989, something remarkable happened. Felipe Gaitan and Lawrence Crum, working at the University of Mississippi, figured out how to trap a single bubble. They used carefully tuned sound waves to create a stable oscillating bubble. One bubble, perfectly controlled, expanding and collapsing 25,000 times per second. And this single bubble was bright. So bright it could be seen with the naked eye in a fully lit room. A tiny star floating in a flask of water pulsing with blue-white light. Single bubble sonoluminescence opened the door to systematic study. Now scientists could measure precisely what was happening. They could time the light pulses, analyze the spectrum, calculate the temperatures involved. What they found was astonishing. The light pulses are incredibly brief, less than 50 picoseconds. A picosecond is 1/trillionth of a second. The flashes are so short that they rank among the fastest events ever measured in physics. Faster than any chemical reaction. Faster than most electronic processes. The spectrum of the light is broad. It peaks in the ultraviolet and extends into the visible range. This broad spectrum suggests extremely high temperatures. The hotter an object, the more blue its light and the wider the range of wavelengths it emits. How hot is the inside of a collapsing bubble? Scientists estimate temperatures of at least 12,000 Kelvin. That is hotter than the surface of the sun. Some experiments suggest even higher temperatures reaching 20,000 Kelvin or more, all from a bubble smaller than a grain of sand collapsing in a glass of water. The pressures are equally extreme. As the bubble collapses, the gas inside is compressed by factors of 1,000 or more. The pressure reaches tens of thousands of atmospheres, higher than the pressure at the bottom of the deepest ocean, higher than the pressure inside many industrial machines. All of this from sound waves in water. The physics seems straightforward at first glance. Sound waves compress the bubble. The gas inside heats up. Hot gas glows. Basic thermodynamics. But when physicists try to model the process in detail, the answers do not quite match the observations. The temperatures seem too high. The light is too bright. The pulses are too short. Something more than simple heating must be happening. One theory involves shock waves. As the bubble collapses, the bubble wall accelerates inward, reaching speeds faster than the speed of sound in the gas. A shock wave forms inside the bubble, converging toward the center. Where the shock wave focuses, temperatures spike even higher than simple compression would predict. This shock wave theory explains some observations, but not all. The mathematics is difficult. The physics involves extreme conditions rarely encountered elsewhere. Computer simulations struggle to capture all the details. Other theories have been proposed. Electrical discharges within the bubble, plasma formation, exotic quantum effects. Some scientists even speculated about nuclear fusion occurring inside the collapsing bubbles. This speculation attracted enormous media attention, but has not been confirmed. In 2002, a group at Oak Ridge National Laboratory claimed to have achieved nuclear fusion using sonoluminescence in deuterated acetone. The bubble supposedly became hot enough to fuse deuterium atoms, releasing neutrons as evidence, but other laboratories could not reproduce the result. The claim remains controversial, and most physicists are skeptical. What is not controversial is that sonoluminescence exists, and that we do not fully understand it. The mechanism of light emission remains uncertain. Multiple theories compete. None is universally accepted. One of the strangest theories comes from Julian Schwinger, a Nobel laureate in physics. Schwinger proposed that the light comes not from hot gas, but from the quantum vacuum itself. As the bubble collapses, the rapidly changing boundary might excite virtual photons in the vacuum and convert them into real photons. This would be related to the Casimir effect and to Hawking radiation from black holes. Schwinger's theory is exotic, but not obviously wrong. The vacuum of quantum field theory is not empty. It seethes with virtual particles popping in and out of existence. Under extreme conditions, these virtual particles can become real. A collapsing bubble creates extreme conditions. But most physicists think simpler explanations are more likely. Hot plasma emitting thermal radiation, Bremsstrahlung as electrons scatter off ions, chemical reactions in the compressed gas. These mechanisms are well understood in other contexts. They should apply to sonoluminescence as well. The problem is that no single mechanism explains all the data. The light is too bright, too blue, too fast for any simple model. Something unusual is happening inside those collapsing bubbles, and after nearly a century of study we still do not know exactly what. This is humbling. We have sent spacecraft to the outer planets. We have detected gravitational waves from colliding black holes. We have mapped the cosmic microwave background, and yet we cannot fully explain what happens when a bubble collapses in a glass of water. Sonoluminescence is a reminder that mysteries remain even in familiar settings. Light comes from places we do not expect. Phenomena occur that our theories cannot fully capture. The universe is more surprising than our equations suggest. There are other unexplained phenomena involving light. Ball lightning, for example. Glowing spheres of light that appear during thunderstorms float through the air and then vanish. Thousands of eyewitness reports exist. A few photographs, some video recordings. But no scientific explanation commands universal acceptance, or consider the precise value of the speed of light. Why is it exactly 299,792,458 meters per second? Why not some other number? The speed of light emerges from Maxwell's equations as a combination of electrical and magnetic constants. But why do those constants have the values they have? Why is the universe tuned to produce this particular speed? These questions may have no answers, or they may point to deeper physics we have not yet discovered. Either way, they remind us that our understanding of light is incomplete. We know more than the ancient Greeks who thought light flowed from our eyes. We know more than Newton who thought light was a stream of particles. We know more than Young or Maxwell or Einstein. But we do not know everything. We may never know everything. Light still has secrets, and that is perhaps the most important lesson of this investigation. The greatest mysteries are not in distant galaxies or abstract mathematics. They are all around us, in the glow of a collapsing bubble, in the flash of a single photon, in the shimmer of sunlight on water. Light is common. Light is essential. Light is the medium through which we perceive the world, and light is deeply strange. Stranger than we knew before quantum mechanics. Stranger perhaps than we can ever fully comprehend. In our final chapter, we will try to synthesize what we have learned. We will ask what light really is given everything we have discovered, and we will confront the limits of human understanding when facing phenomena that transcend our intuitions. What is light? The answer has changed many times over the centuries. It may change again. For now, we can only describe what we have observed and admit what we do not know. Chapter 10. What light really is. We have travelled a long way, from ancient philosophers wondering what makes the world visible, through Newton's prisms and Young's slits, through Maxwell's equations and Einstein's quanta, through the strange experiments of quantum mechanics that revealed a reality beyond our comprehension. Now we must ask the question we started with. What is light? The honest answer is that we do not know. Not fully. Not in a way that satisfies our intuition or matches our everyday experience. We have mathematical descriptions that work. We have theories that predict experimental results with extraordinary precision. But we do not have a picture we can visualize. We do not have an explanation that makes sense. Light is not a wave in the classical sense. It does not need a medium to travel through. There is no ether filling space whose vibrations carry light from star to star. Maxwell's electromagnetic waves propagate through empty vacuum. They are oscillations of electric and magnetic fields. But what are these fields made of? The question may have no answer. Light is not a particle in the classical sense. It does not have a definite location until measured. It does not follow a definite path. A photon passing through two slits goes through both simultaneously. In some sense that we cannot fully articulate, it interferes with itself. It exists as a probability wave until it is detected. Wave-particle duality is not a compromise between two classical pictures. It is not that light is sometimes a wave and sometimes a particle depending on the experiment. Light is neither. It is something else entirely. Something for which we have mathematics but no adequate words. The physicist Richard Feynman developed a way of thinking about light called the path integral formulation. In this picture, a photon does not take a single path from source to detector. It takes all possible paths simultaneously, every conceivable route through space, every imaginable trajectory. The photon explores the entire universe between emission and absorption. These paths interfere with each other, most cancel out. Only paths near the classical trajectory contribute significantly to the final outcome, but in principle the photon travelling from your lamp to your eye has explored every possible path in the universe. It has gone around the moon and back. It has travelled to distant galaxies. It has done everything. This is not metaphor. It is the mathematics of quantum electrodynamics, the most precisely tested theory in the history of physics. Its predictions match experiments to better than 1 part in a billion. The path integral formulation is not a convenient fiction. It is how the universe actually calculates probabilities. But what does it mean? What kind of reality underlies this mathematical description? Here, physicists disagree. The Copenhagen interpretation says we should not ask. The wave function is a tool for computing probabilities. It does not describe what is really happening. There may be no deeper reality beneath the mathematics. The universe only commits to definite outcomes when observations are made. The many worlds interpretation says everything happens. Every possible outcome of every quantum measurement actually occurs. The universe constantly branches into parallel versions. We experience only one branch, but all branches are equally real. There is no collapse of the wave function, only the appearance of collapse from within a particular branch. Pilot wave theory says particles have definite positions at all times. They are guided by a wave function that tells them where to go. The apparent randomness of quantum mechanics comes from our ignorance of initial conditions. Hidden variables exist, but they are non-local. They act instantaneously across space. Each interpretation has its advocates. None can be distinguished experimentally. The mathematics is the same, only the metaphysics differs. Perhaps the problem is not with the universe, but with us. Our brains evolved to survive on the African savanna. We are adapted to track predators, find food, and recognize faces. We are not adapted to understand quantum mechanics. Our intuitions about waves come from water and sound. Our intuitions about particles come from rocks and bullets. Light is neither. It is a quantum object, a kind of thing that exists only at scales far below our everyday experience. We have no built-in intuitions for such objects. When we try to visualize light, we inevitably use classical images, waves or particles. But these images are wrong. They are approximations that work in certain limits. The true nature of light lies outside the realm of visualization entirely. This is not a failure of physics, it is a success. Physics has revealed aspects of reality that transcend human intuition, that cannot be captured in pictures or metaphors, that can only be described mathematically. Some physicists find this disturbing. They want a theory they can understand. They want pictures they can visualize. They want to know what is really happening when no one is looking. Others embrace the abstraction. They accept that the mathematics is the theory, that asking for a visualization is asking the wrong question, that nature at its deepest level may not correspond to any human mental image. What we can say with confidence is this: light is an excitation of the electromagnetic field. It carries energy and momentum. It travels at a fixed speed through vacuum. It interacts with matter by being absorbed and emitted in discrete quanta. Its behavior is described by the laws of quantum electrodynamics. These laws have been tested and confirmed beyond any reasonable doubt. Beyond that, we venture into interpretation. philosophy, speculation. We can debate what the wave function means, whether the universe is deterministic or random, whether reality exists when no one is observing. These are profound questions, but they are not strictly scientific questions. They cannot be settled by experiment. What matters for science is that the predictions work, that we can calculate what will happen in any given situation, that our theory matches observation. Quantum electrodynamics does all of this. It is the most successful scientific theory ever created, and it remains deeply mysterious. We have discovered things about light that no one could have imagined, that it travels at a constant speed for all observers, that it comes in discrete packets called photons, that these photons can interfere with themselves, that measuring which path a photon takes changes its behavior, that entangled photons remain connected across any distance, that choices made in the future seem to affect the past. Each discovery challenged our intuitions, each forced us to revise our picture of reality, each brought us closer to the truth while revealing how much we do not understand. Light is the key to the universe. It is how we see, how we communicate, how we explore. Every telescope looks at light. Every photograph captures light. Every scientific instrument ultimately converts some physical quantity into light that our eyes can perceive. And light is the key to understanding. The study of light led to relativity and quantum mechanics, the two pillars of modern physics, the frameworks that describe everything from subatomic particles to the expansion of the cosmos. Einstein began his career thinking about light. What would it be like to ride alongside a beam of light? This thought experiment led to special relativity, the realization that the speed of light is a universal constant, that space and time are relative, that mass and energy are equivalent. Einstein continued his career thinking about light. What is the nature of the photoelectric effect? This question led to the photon, to quantum mechanics, to the strange dual nature of reality that we have explored throughout this investigation. Light connects everything. It is both the subject of our study and the tool we use to study. It is both the mystery and the key to solving other mysteries, and it remains unsolved. After 400 years of scientific investigation, we still cannot say what light is. We can describe its behavior with extraordinary precision. We can predict its interactions with matter. We can harness it for technology beyond the imagination of earlier generations. But we cannot explain what it is in any intuitive sense. Perhaps that is as it should be. Perhaps the universe is not obligated to match our intuitions. Perhaps nature at its deepest level is simply stranger than we can imagine. The great physicist Niels Bohr said that anyone who is not shocked by quantum mechanics has not understood it. We have tried to understand it in this investigation. We have tried to convey the shock, the strangeness, the wonder. Light is common. It fills every day of our lives. We wake to it and sleep in its absence. We use it to read and write and see the faces of those we love. It seems so ordinary, so familiar. But familiarity is not understanding. We live surrounded by a phenomenon that defies explanation, that violates our intuitions, that connects past and future in ways we cannot comprehend, that reveals a universe far stranger than we ever suspected. What is light? It is everything we have described: wave and particle, field and quantum, energy and momentum, electromagnetic radiation traveling at the universe's speed limit. And it is something more, something we cannot name, something that lurks behind the mathematics and the experiments, something that perhaps no human mind will ever fully grasp. That is not a failure. That is the adventure, the ongoing investigation that began in ancient Greece and continues in laboratories around the world, the quest to understand the most fundamental aspects of reality. We do not have final answers. We may never have final answers, but we have better questions than we did before. We have deeper mysteries. We have seen farther into the nature of things. Light remains unexplained, and that is what makes it so fascinating. If you have made it this far, thank you for joining me on this journey. Thank you for thinking about these strange and wonderful ideas. Thank you for being curious about the universe we inhabit. Please like this video if you found it valuable. Subscribe if you want to explore more mysteries with me, and tell me in the comments what other phenomena we should investigate next. What other questions keep you up at night? What other aspects of reality seem impossible to explain? The universe is full of mysteries. Light is just one of them. But what a mystery it is. Thank you for watching. I will see you in the next investigation.